Morning, folks. I guess it's morning specifically for folks on the West Coast. It just became afternoon for us here in Central Time in Chicago, and then on the East Coast, y'all have been in the afternoon for an hour. Regardless, welcome. Today, we're going to be doing a stream on a confidence interval data visualization that I am working on. As promised, I've got Ozzy here with me. I'll show you. I've got my breakfast here, which he knows he's not supposed to take, but he's trying to sneakily get some of. But I'll do my best to keep him off it. Or maybe I'll get so enthralled. We might get so enthralled in the stream that by the time I look up, he's just done with that thing. One time he stole a whole chicken thigh from me. And he only weighs 9 pounds, so it would be the equivalent of me running off with like 7 pounds of food and eating it. He apparently ate the whole thing. I found no trace of it anywhere. So anyway, welcome. Today we are going to be working, like I said, on a data visualization about confidence intervals. So we're going to be doing this in a tool called Streamlit. And in fact, let me go ahead and show you what we are doing. Hopefully everybody can see this. I'm going to go ahead and minimize my OBS screen so that you can see everything. All right, so I got my terminal here. I've got my chat here so I can see if you say anything. And then I've also got, you'll notice this nice little website up here. This is the local version, but I actually have this deployed as well, right there. Streamlit makes it really, really easy to deploy like data visualizations like this in little sites to demonstrate your data analysis. And I'm going to show you a little bit more about that later. But first, let me kind of walk you through what we've got here. Now, so I'm a teacher, and I teach mobile software development, I teach Python programming, I teach intermediate Python, and I teach some data science and applied machine learning, as well as some workshops on things like analyzing tech debt and analyzing risk in an application. A lot of courses where I'm trying to break down systematically some amorphous concepts that we sometimes have trouble getting our heads around in tech. So it should come as no surprise to you that I like to analyze data the same way. That's sort of where I got it from. And there are a number of concepts in data analysis that I think are really helpful for software engineers and data engineers to know about, almost regardless of how much they're working with data, because no matter how little you're working with data, it's very important to understand the implications of the numbers that you are using when you're attempting to quantify something. And I think one of the most important concepts for somebody to understand who might be using data is the confidence interval. So the upshot of the confidence interval is that when you are trying to describe something based on a sample, the larger your sample is, the more confident you can be in your description based on the example. I like to use heights as an example. So you can't really use your own height as a very accurate example, as a very accurate reflection of the average human height, because you're only one person and there's billions of people in the world. And if you were to just average the heights of yourself and 3 friends, that still wouldn't be very representative of the entire population. But if you were to average the heights of 100,000 people, that might be getting closer. And if you were to find the mean height among 4 billion people, that might be even closer to the actual mean height of the global population, particularly if you were very careful to get a sample that accurately reflected sort of the demographics of the global population. The idea behind a confidence interval is that it's a systematic way to put error bars around your description of some data depending on the size of your data set. So, in other words, the confidence interval around the average height, the average human height based on one person would be very large. 3 people would still be very large. 100,000 people would be relatively smaller, and 4 billion people might be pretty small. The idea with a confidence interval is to be able to say, among the population that I sampled, this was the mean. However, based on the fact that this is how large my sample is, this is the probability with which I think it's actually between some amount lower and some amount higher than this mean, the overall population mean. So, for example, with the heights example, we might be able to say something like, there are 100,000 people in this sample, and the average height among those people is 5'2", and based on that, we think with 95% probability, the global mean height is somewhere between 5 feet tall and 5'4", let's say, plus or minus 2 inches on the average height that you saw in your example population. So that's the idea. So I have this visualization that I've been trying to use to make it easier for folks to understand the concept of the confidence interval. What I'm using right now is Chicago maintenance data. And so we have all these different maintenance categories in Chicago: alley grading, the lights being out, potholes, cable getting cut, pavement buckle, pothole in the street. And we know how many days it took to respond. We also have an average of the days that it took to complete each of those jobs. And we know how many times each of those jobs have been done in the data. And so I've been demonstrating confidence intervals on this data. Now let me show you the Streamlit code because this is actually quite cool. So let me hop over to my pie chart and let me check on the stream to make sure that you're still able to see everything okay. Yeah, it seems like you can. Okay, so this is my Streamlit code, and you'll notice that for that entire site I've only got about 73 lines here, and a pretty big chunk of it is just displaying a chart, which I will show you in a second. So what Streamlit does is it attempts to make it really easy for us to be able to publish sites to demonstrate what's happening with our data analysis. So in this example, you can see that I've got the data depicted right here inside of this data frame. I've also got titles on here and text explaining everything. In Streamlit, here's how that looks. I can import Streamlit and then do st.title, and that gives me the title in the format that I want. Then I just have a string here that maps to this string right here. Today we'll be looking at how long it takes the city of Chicago to respond to various maintenance requests. Here's the data we'll explore. Now, the interesting thing about Streamlit is that you can write just about anything to your Streamlit page by doing st.write and then putting it in here. Here is some text, right? So let me show you how that looks. If I jump over here and I refresh my local, here it is, some text. Now, that having been said, with Streamlit, when you have something just on a line by itself like this, Streamlit automatically writes that for you. If you have an expression, Streamlit automatically writes that for you. And that's why we can have just this string right here. We have a number of them down here as well. I compare that a little bit to the Jupyter Notebook, where things are a little bit more explicit. You have markdown cells and you have code cells. You don't have that in Streamlit. Everything's kind of mixed together, and you don't have to delineate specifically what's supposed to be text, what's supposed to be code. Rather, Streamlit attempts to infer what you want it to do with each thing that is in your script. Mister here has got his paws on my breakfast. Get them off. All right, so we're going to go into a little bit what all is happening here, but first, the reason that this data frame is showing up right here is that I have the aggregation on its own line right here. Aggregation is the result of a function called load data, which I have up here and we'll go over later, where I'm effectively loading some data out of a CSV, and I'm running some data frame manipulations on it. This is plain pandas code. If you've used pandas before, you've absolutely seen exactly something like this. And so because that aggregation is on its own line, it gets written right here. Now, automatically, we get some pretty cool stuff. For example, I can scroll through the data up and down, left to right. I can also automatically click on the column names and get it sorted by whatever that column is. I can click on target response days and see at the top which of these items had the shortest target response days or fewest number of target response days, and scroll down as well. I can flip the order of the sort by clicking back and forth on the same column. I can do that by any one of these columns, which I think is pretty cool. So I can see, for example, the one of these that we have logged the most is a pothole in the street. If you're familiar with Chicago, that won't be surprising to you at all. The second one is sign repair. And they're almost the exact same number, which paints a pretty funny picture of somebody bouncing off a pothole in the street and knocking down a sign on the way. So that's our data basically, and then I have a number of texts here as well, and you can see those in the Streamlit code as well. But then comes the interactive part, and this part I think is really cool. So what I'm attempting to do here is demonstrate how confidence intervals work based on two variables that you can change. So the first is a percentage of the data to use. Now, like I said, if you have more data, your confidence interval can be more narrow because the amount of data as it grows gives you a better representation of a total population. It gives you a better idea based on how much data you have of how accurate your predictions about a larger set would be based on the set that you've got. So I have percentage of data to use here because with this data up here, I'm attempting to simulate having more data or less data by allowing you to use more or less data from the data set. And every time we change this percentage of data to use, this chart down here updates. So what this chart shows is all of the different maintenance activities that we have in our data. And the blue dot represents the mean number of days that it took to complete it, to complete those jobs. And the two red dots represents the upper and lower bound of the confidence interval. Now, it's a little bit tough to see how these things are changing because the dimensions of this, the number that the x-axis goes up to here changes depending on what the max number is in the data, and so it's a little bit difficult to see how these dots change relative to each other. That might be something that we try to fix in today's stream. But, for example, if you were to look at any one of these blue dots, as we increase the amount of data we're using, the red and the blue dots the red dots around the blue dot get relatively closer together. So that is one variable that impacts the confidence interval. Another variable that impacts the confidence interval is the probability of the true mean falling between the red dots. And so with confidence intervals, the default for this tends to be 95, meaning that generally when we represent, let's say, a mean with a confidence interval, that confidence interval represents a 95% probability of the true mean falling inside of the confidence interval around the mean that we've expressed. And that's why this slider is set to 95. But you can move it down, and the idea is that you should be able to see the red dots moving further out from the blue dot. And right now our chart's getting like a little bit thrown off because we have these two dots down here that have these like basically further right skews, and so that changes sort of the dimensions of all the rest every time they change. Like I said, that might be something that we try to fix on this stream. So this is a start, and what I would like is for people to be able to interact with these two sliders and then see the chart change and understand better how confidence intervals work. Right now it's not 100% illustrating this concept to the degree that I would like. But before we get started, I want to show you a little bit more about the Streamlit implementation of this, which is how I get it to change. So this right here is plain old matplotlib chart. I've got scatter plots that basically demonstrate first the mean, and then the lower bound of the confidence interval, and then the upper bound of the confidence interval. Okay? And every time the sliders change, those sliders are right here. So the way that these sliders work, let me make this bigger so that you can see it better. The way that these sliders work is that they have a label, they have a bottom amount, they have a top amount, and they have a default amount. And the variable that we assign it to equates to the value at wherever the slider has been slid to. And every time these variables change, that is when the slider slides, for example, anywhere that uses that variable gets reloaded. So, for example, in this case, I've got this function called update metrics that takes in the amount of data we're using and the confidence. The result of update metrics includes the number of examples we're supposed to use, the bottom of the confidence interval, and the top of the confidence interval. And we use those things here in our scatter plot. So the scatter plot reloads every time we move the sliders. And there are a number of interactive components like this in Streamlit. We can do buttons, we can do checkboxes, those kinds of things. If we keep doing more interactive data visualizations with Streamlit, you'll get to see more of these. So let's, so we've got our sliders, right? And we've got our function here, and we've also got our chart. Let's take a look at the functions real quick. Because there are a couple of interesting things about this that I do want to show you. The first is the loading of the data. Now, we talked about this a little bit. I'm reading some data out of a CSV, and then I'm doing an aggregation on it, which effectively does some manipulation in order to be able to collect the target response days for a specific activity, the mean days to complete activity, and the number of times that that activity has happened. Now, this is a relatively large data set, and so this kind of takes a long time. In order to ensure that we don't have to do that every single time we reload, I can put this Streamlit cache decorator on it. And what that Streamlit cache decorator does is it ensures that if I am calling this function the same way with the same inputs as I did prior, then it will use the cached result for that rather than rerunning the function. And the result of that is going to be that on future loads of the page, this loads really quickly, whereas the very first time it loads relatively slowly. Now, there's a caveat to be aware of that with the way that Streamlit works, which is that if you are then changing something that gets manipulated by the cache, you can end up in kind of a troubled state. So, for example, I've also got this update metrics function. What the update metrics function does is it changes the numbers that we are using for the chart. It changes the numbers that we are using for the chart every time we slide one of the sliders. Now, originally, the way that I was doing this was that I was updating my aggregation data set. And so I would say aggregation num samples, and I would save this off as a column, and I would update the column. So let's do this, and you will quickly see why this is a bad idea, I think. All right, so I've got this, right? So now, instead of making new variables there, what I am doing is I am updating something that I create out of this cache. And when we reload, here, let me do it this way. Num examples, we now want to use, where is num examples used? Confidence interval bottom, confidence interval top. So now we would want to use those columns that we made in the data rather than using these variables. Confidence interval top. All right, so you get this cached object mutation warning. This says the return value of load data was mutated between runs, meaning, okay, you've got this cached function, okay, and you return aggregation from it, which theoretically every time you call load data, you want to return that same aggregation, except that you modified the value of the aggregation, which means that the cached one is now different from the one that you are using. And so if you try to use the cached one with the modifications that you added on top, the cache is not updated. You're not going to get a hold of those additional changes you made on top of your cached thing. So Streamlit goes on to explain, by default, Streamlit's cache should be treated as immutable or may behave in unexpected ways. You received this warning because Streamlit detected that an object returned by load data was mutated outside of load data. So for that reason, we don't want to be mutating whatever our return value is of something that we are caching. Instead, we want to either save that stuff off as new variables, or we want to reevaluate whether we should be using the cache on a method like load data, on a function like load data. So I wanted to show you that because I think the error message is very clear and very descriptive. That having been said, if you've only seen it the first time and you're not 100% clear on how this caching functionality works inside of Streamlit, it's something that can be a little bit jarring that first time. So there's that. So like I said, we've got this update metrics function, and as you know, I am calling that down here such that every time these two variables change, it gets called again, which then changes these variables, which we then use down here, and so our plot updates. Now, there are a couple of problems with this as far as I'm concerned that I don't really like how it works. Let's, hold on, I have to fix something here still. Wait, easy. Am I still using a value somewhere? I don't think so. I might have to reboot my my Streamlit thing to get rid of that. Let's give that a try. Let me shut this. Do Streamlit run confidence intervals chart. This is how you run this thing. It's pretty great. Waha! The error's gone! Okay. So let's talk about this chart a little bit, because I've got some problems with this chart. So the first problem that I have is that these numbers don't stay still. And I'm not sure how to fix that yet, but maybe we'll figure that out a little bit later on the stream. I want the mean, I want it to be obvious how the confidence interval is changing as we change these two sliders. And right now, it isn't. The interactivity portion is there, but the clarity on the data visualization is not there. Give me just 1 second. I need to take care of one thing. Okay. Okay, so that's one issue that I have with it. The other is that this data, I wanted to use like real data if I could. So my first run at this was to use some data from the Chicago Open Data Portal, which normally I would like to do. But one thing about it is that it doesn't give you each individual instance of alley grading. Instead, it provides you with the instances kind of bucketed by week, and so it'll say like 7 of these instances happen in this week, and the average amount of time that the job took was this amount of time. And so we already don't have the individual instances, we just have aggregations. And for that reason, I can't actually recalculate means based on how much data I have. And I think it might be instructive to be able to see how the mean moves based on the amount of samples that you have, but I can't do it. I've been just keeping the mean in the same mean, and then essentially passing the confidence interval function, which I can show you, a different number of samples to indicate make the confidence interval bigger. So I've been just updating the sample size effectively. but I have not been changing the mean. I've just been using the mean based on all of the data that we originally had. So this isn't 100% accurate. And I think that's not really an accurate demonstration of what's happening here. The other thing is that when these sliders move, it really takes a minute to reload. And the reason it takes that long to reload in part is because this data set has really a lot of data in it. And so the data munging part takes a second, which is fine, but I think that lag is, ideally there would be less lag for the purposes of this illustration demonstrating what I want. So I decided this data set isn't the data set that I want to use for this demonstration. Although I like to use real data where I can, in this case, this real data is missing some of the qualities that I think would really make for the most helpful possible educational example. And so I fabricated a new set of data. And that set of data is called toxicology data. And what it does is it simulates readings of the amount of a fictional toxic substance in water at fictional locations on various days and various times of day. So the first thing that I would like us to do together is switch out this code to use this data instead of the data that it is currently using. So let me make this a little smaller again and get rid of this extra. Ah, somebody says hello. Hi, Ali Akbar. All right. So let me actually make this a little bit smaller so that so folks can see. Okay, so this is going to be the data that we're going to be using now, which means that we need to change out in our confidence intervals chart what we are doing in load data. So the first thing is going to be that we're going to change metrics.csv to toxicology data.csv. And now these all of these values are going to change. So the toxicology data, sorry, 1 second. It has been a day, y'all. There's like a meat shipment going wrong, and so I need to take care of that. We'll text you when it's there. We'll go in 20 minutes or so. All right, perfect. Okay, so what columns do we have? We have date, time of day, assessor, location, and reading. Right? Date, time of day, assessor, location, and reading. So here's the reading. Right? So we're going to copy the name of this. Because ultimately what we want to be able to do is group by the location. Okay? Group by the location and get an average reading. So that's what we want. So let's see how we would get there. So we've got our toxicology data, and we're going to want, instead of mean days to complete this activity, it's going to be mean reading. And then we want the reading in parts per million. And actually, we might want to do this in the aggregation. Yeah, mean reading. I think. Because we want to take, we have this row, reading parts per million. Yeah, this is what we want. So what we're going to do is we're going to group by location. We're going to group by location. Let me make sure that it's called location. It's called location. I really like to copy and paste these because inevitably I type something wrong. I'm like a worse typist the longer I'm a programmer. We actually don't even need this line. So I'm going to group by location. I want the mean and standard deviation on the reading in parts per million. And then I want, for location, I want the count. Do I want the count? I think I want the count, because that's going to tell me how many readings we have at each of these locations. You'll see that a lot of the locations are Hogwarts ones. For the record, this is not an endorsement of J.K. Rowling or anything she has said. This is, I wanted obviously fictional places because the data is called toxicology data, and I didn't want anybody to accidentally get under the impression that any of this data really represented like the water being poisoned where they live or something. Okay, so we're getting location count, reading in parts per million. I want the mean and the standard deviation on that. And then the location count, we're going to reset the index. This is standardizing the way the columns look. And that's going to return the aggregation. So let's go ahead and comment out our update metrics thing, our sliders, and all this stuff, and see that our data looks the way we expect. All right, let's take a look. There'll definitely be something wrong. Toxicology data. This is why I copy and paste everything. Toxicology data. Okay, ready to try again? Wow. All right. Check this out. So, I have got a location. Chamber of Secrets, Forbidden Forest A, Forbidden Forest B, Hogwarts School, the Leaky Cauldron. All right, I got all these things. So I got the reading in parts per million mean. I've got the reading in parts per million standard deviation. And I've got the location count. So I want you to notice something about these means and standard deviations, right? Is that we've got these means, right? And we've got these standard deviations. And the means represent where the middle is. And the standard deviations represent the variance, how like separated from the mean different points are. And so if you've got points that are more spread out, then you'll have a higher standard deviation than points that are closer to get, or where standard deviation. This is the mean, this is the standard deviation. This is where the middle is when we average the points, get their mean, and this is how spread out those points are, a representation of how spread out the points are. We also have the location count, so you can see for the Chamber of Secrets, we only have a few readings. For Nocturne Alley, we also only have a few readings. For School Grounds and the Leaky Cauldron, we have more readings, and then for the Forbidden Forest, we have quite a lot of readings. That will impact our confidence intervals. All right. So how will it impact our confidence intervals? So the location count, as we've discussed, your confidence interval will be wider if you have fewer readings. Additionally, your confidence interval will be wider if your standard deviation is higher in order to accurately capture how spread out the points are, which indicate more variance. More variance can mean that your data in a sample may reflect a full population mean even less accurately. So now let's go in and we'll try to put our chart back. Let me make this smaller again so I could see if anybody puts anything in the chat. All right, so now we're going to add this back in. And the way that we're going to do this is we are going to get a sample, a random sample of the original data based on the amount that we want to use. So how are we going to do that? Because we already aggregated it up here, right? So actually, we're going to have to move this down. Yeah. So this is going to be sample of data. And then sample of data will be, do we want to use a representative or a random sampling of the amount of data that we have for each of our locations? I think I want to start with just a random sampling of all of it and see what that does to our chart. My bet is that sometimes the Chamber of Secrets won't even show up because in a random sampling it'll be relatively likely for all 7 Chamber of Secrets samples to be missed, which I think would be kind of fun to look at. So let's try that. So I'm going to do sample of data is going to be equal to, so we're going to pass in data, and then the sample of data is going to be normal sampling. Do you know off the bat how you would do that in pandas? I'm going to have to look that up right now. So let's do pandas sample of rows. Haha, a sample. All right. So you can sample based on a fraction. We can set a seed, evidently, which is helpful. I think we want to use this fraction one, so let's try that. Okay. Data sample. Ali Akbar, do you know how we would do that right off the bat? This is going to be data amount. It's going to be this thing right here. Yeah. So we're going to do a sample, and then we're going to do all of this aggregation stuff. And then get rid of this return. Unfortunately not. It's okay. We can come back to it. If we get everything else figured out, then that is an improvement that we could absolutely do. Here, let's do return. All right, so this is now going to be called data. Data. In fact, let's call it full data set. Full data set. And I don't want to keep changing the full data set. So we're going to do our chart based on the sample data set. And let's call this sample data set. I'm a big fan of consistency in my names. All right, so I'm going to get this data amount, and the data is going to come in as this, so it actually has to be divided by 100. And so in Python, if you are doing an arithmetic operation between a float and an integer, your result's going to be a float, so we don't have to account for that. I'm not positive how it used to work in early versions, but that's how it works now. So we've got our aggregation columns, that's fine. So the number of examples is not something that we need anymore, because we were doing this with those like aggregation numbers, which is not what we want. And so now we're going to do aggregation, location count, I believe. And we actually don't need num examples in our return either. The standard deviation is going to be aggregation of let's see. So let's actually print these both out. So this is going to be st.title full data set. And then we'll do st.title sample data set. And we will do this down here. So wherever our sliders are at, yeah, there's our sliders. So we're going to do sample data set, and then we'll do return let me think about this. Let's put these two things on our aggregation, which I want to call shift sample aggregation. And then let's add sample basically for both of these. We're going to assign it back. Sample aggregation is going to go, yeah, so it's going to be conf interval bottom and conf interval top. We're going to assign those two columns in, and then we'll be able to look at them. So we have our confidence interval for collection, blah, and then we're going to return our sample aggregation. Then down here, we won't worry about the rest of that for right now. So the first thing we'll do is start with a data amount of 60 and a confidence of 95. And we'll do, let's see, the sample data set. Do we need the columns? I don't think we need the columns. Let's do update metrics full data set. And we're going to start with these two values, data amount equals 60 and confidence equals 95. And we'll say sample data set, which is the same name as we use up here, but this one is scoped only within this function, and so this one is scoped outside the function. Let's see if that loads. There's no way I did all that right on the first try. None. We got our full data set. Cute, very long. Sample data set, mean days to complete activity, standard deviation. So this is not right. Oh yeah, this is definitely not right. So this is going to be reading parts per million STD. Yes, these column names are they've got spaces in them and they're fragile. This one's also going to be reading parts per million mean. Okay, let's try again. Okay. So we got our chamber of secret stuff. We've got our reading in parts per million. So here's one thing that you're going to notice is that these means are changed from what we saw when we were using the full data set. You're also going to notice that the location counts are down. And the reason the location counts are down is that we are now only getting a sample of the data, right? Not all of it. So these ones that we have 200 of, we're now only getting about 60% of that. The ones we had 100 of, we're only getting about 60% of that. A little more, a little less, right? So then we've got the reading standard deviation, the reading mean like we had before. We've also got this bottom of the confidence interval and top of the confidence interval. You'll notice the bottom of the confidence interval is always less than the top of the confidence interval because what's happening is that the confidence interval to get the bottom is subtracting from the mean. and to get the top is adding to the mean. So now let's try to add back our chart. I'm scared. Are you scared? I'm not scared because I have any actual reason to be scared. I'm just scared because I'm a nervous person. All right, so we got our full data set. We've got our sample data set. I want to say sample data set with blah percent of the data. And that's going to be amount of data. Amount of data. Does Streamlit support F strings? We are about to find out. Slider. Sample data set with 60% of the data. It worked. And then when I slide this, it recalculates. So this is a little bit faster than the other one was. And the reason is that the other one has like the other one being the alley grading, the Chicago maintenance data. Reason being, this data only has 600 rows in it and the other one has several thousand. I am okay with the fact that we're using less data for this demonstration because the whole point here is to demonstrate how confidence intervals work. It's not to do like actual data analysis on a production data set. This is better. Yeah, so check it out. The mean is changing. And the reason the mean is changing is because when you're taking like random samples, right? What ends up happening is that your random sample mean is going to be like a little bit different. Because we have a relatively small data set, those means are in fact changing quite a bit. Let's see how the location counts change. So far, I actually have not seen the Chamber of Secrets not come up, which surprised me a little bit. This seems off because I would expect the location counts to be lower at 26% of the data. So you might need to spend some time figuring out what's going on there. All right, let's try putting our plot back in. Let's call this st.title confidence interval plot. And let's move our slider down. Probability of the true mean falling within the confidence interval. All right, so let's make sure our slider shows up. So we've got confidence intervals visualized on fictional toxicology data. Today we'll be looking at how long at fictional data about the presence of a toxic chemical at fictional reading locations. All right, let's make sure I like to make sure all of our confidence intervals visualized on fictional toxicology data. Today we'll be looking at fictional data about the presence of a toxic chemical at fictional reading locations over time. Here's the data we'll explore, full data. We'll look at the mean. Amount of chemical present across readings. And a mean means a lot less when it's based on just a few data points than it does when it's based on many data points. We can account for this with a confidence interval, which sort of represents the error bars around a mean. Less data, larger error bars. More data, smaller ones, because we're more confident that the mean of a lot of data represents a population mean. And I will say represents a population mean or true mean. Here we go. So let me go ahead and update that. We can account for this with a confidence interval, which sort of represents error bars around a mean. The reason it says an, I think, is that I had average there for a while, and I decided to use the term mean. Yes, this chart shows the mean project length for each type of project with a confidence interval around it. Okay, so this is going to change. So this is going to say, this chart shows the mean toxicity reading for each reading location with a confidence interval around it. This chart represents A, and we'll put confidence. %95 in this case probability that the true mean falls within the red dots. And I'm not sure I like the dots thing, so we might go back and adjudicate that too. Can st.write adjudicate an f string like that? Let's find out. It can. This chart shows the mean toxicity for each reading location with a confidence interval around it. We'll say it represents rather than this chart twice. All right, so let's do our confidence interval plot now. We add this back. We're going to have to change some things about this. So first of all, sample dataset is going to be, we update the metrics, we pass in the full dataset, so we're not going to need this line anymore. Well, are we? We are. So we're going to have our examples, right? And then we're going to do sample data set here. And then we're going to pass in amount of data, which comes from one slider, and confidence, which comes from the other slider. And this one up here is just going to use the defaults. I think this is going to work. Or at least it's going to use the defaults in the beginning. Okay. Plot. Figure. Plot.figure. Blah. Okay, so now we need to use the mean, and that's going to be the reading parts per million mean. And then it's going to be, so everywhere where it says aggregation, we're going to change that to sample data set. And then for confidence interval bottom, we're actually going to say, so this is what we named both of these columns in sample data set. Is it going to work? Moment of truth. There's no way I did this right the first time. Confidence intervals visualized on fictional toxicology data. Full data set. Sample data set with 60% of the data. Probability of the true mean falling within the confidence interval. I would like to make these titles like a little bit bigger. I'm not sure why they are so small. There's got to be a way to change them. I don't 100% know it, but we can check the documentation and see what's going on. Wah! Reading parts per million. Yeah, it doesn't. Why, where am I doing reading parts per million? Ooh, the sample, this is going to be location. Everywhere. This is going to be location everywhere. Location. That's not the error that we're seeing, though. Column reading parts per million doesn't exist. And that is happening at somewhere. Let's find it. Is that the one place that we're using it all by itself? So something is happening where we're getting from the sample which is supposed to have the reading as parts per million. Every time this gets called, what if we did this? Because we can treat full data set as immutable. I'm not positive that's going to fix it, though. All right. Unsupported operand types for string and int. Maybe it's deleted after aggregation. Let's take a look. Deleted after aggregation. Because right now, what is data amount? Oh, are we passing in? I'm not sure that this is the issue. But, so when we update the metrics, you see how we pass this in? I think what's happening is that we no longer have that column. Because in sample dataset, we don't put that column in. So this needs to be off the full dataset. It should never be we should never be calling update metrics off of the sample dataset. It should always be off of the full dataset. So we have load data, we get the full dataset, we show it off, amount of data, we update the metrics. We're not going to pass in the full dataset. We're just going to not pass in anything. And then that's going to be our sample dataset. Later, we update the sample dataset metrics with new slider values, but we keep using the full dataset as the starting point. This is probably why we were getting something weird with our numbers earlier, too. Oh my god. Oh my god, y'all. Oh my god! What if we make this chart a little bit less tall? It's like too tall, and I can't see what's happening. I also want to make these fonts here bigger. I always have to look up that kind of thing in Matplotlib, but if somebody knows it off the top of your head, I would be more than happy to like stick in whatever it is. All right, I think we can make it even less. Let's try 6. Even more squat. Yeah, I like that. Okay, great. So check this out. I asked this question right here Based on this plot, which projects do you think have only a few data points and which ones have many? We have to change that because which locations, it's like which locations only have a few readings. But you can already see it from this chart because we know that Chamber of Secrets has the fewest readings. And it's like by far the biggest here. Confidence interval, right? And then all of these are teeny by comparison. So if we were to change probability of the true mean falling within the confidence interval to less, we should see wider separation, and we do! Y'all, this is so exciting! And then, if we make the percentage of data to use also less, the confidence interval should further grow. And I think they do. It's a little bit hard to tell once again because I think that this bottom one like kind of skews everything. This is definitely clear though. Well, maybe. We can make the probability really small. Whoa! Alright, it looks like... So this updates... I don't know if this updates faster or slower than the other one. But I think this data is a much better data set for demonstrating what's happening. So now I would like us to take a look at this location count thing, because the full data set has, what is it? 6 locations, and there were 200 plus 200 plus 200 is 600 plus 7 plus some more. There were like 700-ish data points, a little over 600, and 31% of that is somewhere in the 200 range, and we clearly have more total locations than that going on. So I think there's got to be something happening wrong in the way that we are calculating the location count. So let's go take a look at that. One thing I do want to figure out though, so we got our full data set, and then we have to get the count. So this is location count. Our sample data set is the full data set at the sample. So let's do, so that divided by 100 should be 0.6. We group by the location. And we aggregate by the count on each location, which should be right. Any thoughts? Any ideas? Let's see. We take in that location count, take in these standard deviations, take in this mean. Doop-a-doo, doop-a-doo. Let's print out let's look at how many rows there are. Let's just confirm that this is an actual issue. Okay, 642 rows. So if we use 50% of it, we should come out somewhere with 320. Is this just happening because Chelsea Troy can't count? Okay, so 121 plus 104. That's what, 225? 225. 230. 298. 325. 385. 385 divided by 642. It's about 60%, which seems not right. Let me do some more runs and see what we come out with. All right, what is it here? Let's do this. We're going to use Python because we can. 3 plus 122. Ooh. 122 plus, it might be one step behind the slider, you may be right. 121 plus 60 plus 24 plus 55. That's 385, which I think we just established is about 60%. Okay, what happens if we do it again? 4 plus 121 plus... I mean, this is certainly going to explain why we're not seeing the changes we're expecting when we change the sample slider, if this is always the same. 385. We're always getting the same number of samples, and it's always 60% of the samples. All right, why? Why? So we've got this slider, percentage of the data to use, 60. That's great. That's amount of data. So we load the data, and first we update the metrics with amount of data equals amount of data. Confidence equals confidence. I'm wondering if this was always running the defaults, and so it was setting everything back every time we reran the notebook. Okay, so we'll set confidence there. It doesn't matter because we're setting it to the default. All right, so were we just setting it back? We might have been. Update metrics got an unexpected keyword argument amount of data. I totally didn't call the thing that. Data amount. Data amount, y'all, I called it. Let's do this. Let's change this to amount of data. Keep it consistent. All right, we're trying again. We're trying again. Never fear. All right. All right, so we got 60% of the data. I mean, that looks like 385, but let me just check. 6 plus 119 plus 121 plus 59 plus 20 plus 60. Whoops. 385. Okay, so now that looks like it worked. So I think what was happening was that because we had this top one right here that was always... like, we weren't passing in the new values to our sample data set, which we were then reusing. And so it turned out that our percentage of data to use slider wasn't getting used in sampling our sample data set. We might have figured it out, y'all. 218. What is 218 divided by 642? 33.9%. I think this is working better. Okay, now let's look at our little averages. So if we do this with more of the data, it looks like the confidence intervals get bigger. And if we do it with less of the data, oh, well, then the confidence intervals get really big. And then they get smaller when we have more data. Oh my gosh, it sort of works. And then when we move our percentage down, we should see again closer confidence intervals, because the probability can be lower that they contain the true mean. Yeah, closer. Whereas out here they have to be really wide, right? Because if we want to make sure that they contain the true mean, then they have to account for more potential error. Whereas if they don't actually have to contain it, they can be right on top of the actual mean. All right, so now this chart is doing what we would expect. Let's put the values of those two sliders below this title just one more time to make the visualization super clear. Confidence interval plot. And let's put using amount of data to express a probability of the true mean falling within the confidence interval. And this is actually chance, not probability, because probability is between 0 and 1. Okay. F-string empty expression not allowed. Where did I use an empty expression? Here, because I didn't put confidence. Okay. Using 60% of the data to express a 95% chance of the true mean falling within the confidence interval. Great. So, let's now do this. Slide the following slider to use more or less of the data and see how that changes the confidence interval. And then we're going to do the same thing above the other slider. Most of teaching is stuff like this. Slide the following slider to make the probability, the confidence interval, capture the true mean with higher or lower probability, and see how it changes the width of the confidence interval. And we'll say that here too, width of the. All right. Slide the following slider to use more or less of the data and see how that changes the width of the confidence interval. Beautiful. I wonder if we can make those bold. Streamlit. Right, bold. Bold font. Display a metric in a big bold font with the optional indicator of how the metric changed. Oh, I see. You can put metric like that. I do not think that is what we are supposed to be using metric for, so I'm not going to do that. Let's look at st.write. We may not be able to like bold and italicize stuff. What if I do italic? No. Emphasis? Nope. All right, well, maybe we'll leave it for now. Color. That is a chart coloration. This is kind of cool, though. Let's try using that. So you do your label, and then you do your value. Great, let's try that. Where are the sliders? Label. Amount of data. Let's make another one for where's the other slider? Let's start grouping these a little bit. Because this is metric, not title. And then we're going to put this all together. We'll put these together. Does that impact the way it looks? Let's find out. No, it doesn't impact the way it looks. Well, there's our using percentage of data metric, which is cool. Let's make it an F string with the amount of data. And then, whoops, percent. Whoops. I'm not positive that's going to work. And then let's get the delta color. Well, what is... Oh, I see. You have to pass in what the delta is. Gotcha. So you would have to hang on to the old value. Well, let's just see what happens if we add it. My suspicion is that nothing happens because we didn't pass in a delta value. Whoops, 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 whoops. We'll find out. Yeah, nothing happens. Okay, well that was a cool experiment. Let's remove it, because we already have, I think, what we need there. We got our full data set, sample data set with 60% of the data, confidence interval plot. So I think that this is starting to look pretty good. The last thing I want to try is changing this from pure scatter to a box and whisker plot. I'm not sure I'm going to like that. But let's try it. We're going to try it. The thing about these plots is that they handle the data aggregation for you, and that's not what I want. Add whiskers to scatter plot matplotlib. Ooh, add error bars. Yeah, use error bars in a matplotlib scatter plot. Yeah, that's what I want. I want that. So we can do plt.errorbar. Yer. Scatter. See, I really wish that there were labels on things, because in this example, it's not obvious sort of what the, like, which of these axes is A, which of these axes is B. I can figure it out by staring at this, but adding some errors in the X value. Okay, so you can do it the other direction too, which is what we would do. So it looks like you add the error bars, you do the same thing you did in scatter, and then you add the X error. Okay, let's try it. Error bar. These two things. And then that. Get rid of this. And this is going to be, in either direction, luckily the confidence interval is the same. Distance is the same. So this is going to be the difference between the mean and the bottom of the confidence interval in either direction. Let's try it. I'm not sure, y'all. Let's see. All right, well, that is not exactly what we were after. I mean, I think it's close. We just have to figure out why those red lines are appearing. Parts per million mean, location. This is supposed to be a scatter plot. Why isn't it showing up for them that way? Hold on. Let's get rid of this. Plot.scatter. Plot.error bar. They're using PLT. Should we try that? See how I'm using axes? I feel like this is not the problem, but okay. Yeah, this is not the problem. It does simplify the look, but it's not the problem. PLT. Anybody know what's happening here? Let's make sure we still have a scatter plot without this, which I'm pretty sure we do. Yeah. So then if we add, oh, what if we have to take this off? I don't think this is right either. Okay, so obviously the error bars are the issue. Error bar. Let's try what they did. FMT. I always have to look up exactly what these are doing. Cool. Can I change the color? Whoa, 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 whoa. I can. I just have to do. Let me put the scatter on top of the error bars. Not effective. Let's take a look at some of the others. Is there one where the colors are different? Scatter plot with error bars, different colors, matplotlib. We're going to call this the last thing we're doing. And after we do this, I'm going to show you deployment. Oh my gosh, that is a lot. We've got the error. I think we're very close. I love the colors. Some of these seem like they're PyLab charts, though. Here, let's take a look at this. Oh, wait. I think I saw it. I don't think this is right, actually, because I think they want the... This is asking for different color error bars within the chart, if I'm not mistaken. Yeah, check that out. And that's not exactly what we're after either. Let's take a look at it again. Not that one. If we take the scatter out completely, what happens? We just don't have the dots? We do have the dots. Well, what happens if I look at the plt.errorbar documentation and look at all the things you can do? The data positions, the error bar sizes, the format for the data points. So that's going to be, I think, 0 and make them blue. Make them blue circles is what that should do. I'm going to have to remind myself how to do formatting. Let's look at how to do formatting. The optional parameter format is a convenient way for defining basic formatting like color, marker, and line style. Shortcut string notation, described in the notes section below. What notes section? There we go. Format strings. It's marker, line, color. Color, marker, line. Each of them is optional. If not provided, the value from the style cycle is used. Exception. If line is given but no marker, the data will be a line without markers. Other combinations such as color, marker, line are also supported, but note that their parsing may be ambiguous. So this is a circle. So maybe I put them in the wrong order. No, this looks like it's right. Well, if we do this, then what happens? No. Circles that are blue, we think, that are not blue. Let's take a look again. Maybe so if I pull this out, and we may have to take another look at the error bars documentation to figure out what's going on. All right, so that works. And then if we want the error bars themselves to be read, the format for the data points, the color of the error bar lines, E-color. E-color. This is actually a matplotlib formatting stream. That's okay. I think we might have it. I think this might be it. Yay! We got what we wanted! Alright, so now we have our title, our description, our full data set, our two sliders that allow us to change how much of the data we're using, and what likelihood the confidence interval has to contain the true mean, such that less data is going to mean larger bars and higher probability that the bars contain the true mean also means larger bars. We have our confidence interval plot that auto-updates. And we've got our further reading question down here. Great, so you can see how our changes map from our full data set to our sample data set to our data visualization. I'm pretty happy with this. So let's go ahead and deploy it, and I'll show you how to do that because it's super easy in Streamlit. So what I'm going to do is I am going to go to my Streamlit folder, and I'm going to go to my confidence intervals thing. I'm going to add everything. And I'm actually going to remove the other file. switch from Chicago maintenance data to toxicology data and improve visualization. So now I'm going to push this. Alright, so the way that Streamlit works is you go to streamlit.io. Give it a second to load. In the meantime, let me clean up some of this documentation that I used. Oh, there we go. So it shows you my apps. This is the app. And if I were to go ahead and go to this, you can see that it already possesses my changes, because when I push to GitHub, the deployed application picks up my changes. Now, I'll put this link in the chat. You can go and visit this app. So it's super quick to be able to deploy a demonstration of some data analysis that I've done, for example, to the public web, as long as I've got a public repo, and Streamlit will take care of that for me. So the way that that looks on the back end is that I have this list of apps, right? So I've got the Streamlit example. Streamlit will provide this for you, and what it will do is it will fork a repo to your GitHub account that demonstrates exactly what the format needs to be, which is effectively the demonstration has a Streamlit app, or a Streamlit script rather, at the root, and then there can be some other files in there to support it if you like. And you can see my structure here is I've got confidence intervals chart.py at the root, and then I've also got my data functions that I import. I've got my toxicology data that I use. So in that way it works very similar to the way file systems typically do. So Streamlit can sort of try to guess which where your script is inside of a repo like this one, if you've only got one file that is importing Streamlit, which I do. And you'll see that represented. So for example, if I were to try to make a new app, all I have to do is tell it where my repository is, what branch I want, and then main file to path. It tries to guess, right? And it's doing that based on the fact that I've only got one file in there that imports Streamlit, is my guess. I'm not actually going to deploy this, because it's exactly the same as the application that I already have deployed. But from there, I would hit deploy, and then this page would show me this really pretty cute weight cursor with cookies and cakes and stuff, and it would switch through the cookies and cakes until I had a deployed application just like this one. So I'll put the link to this application in the show notes as soon as I am done with the stream. But other than that, I think we made some good progress today. Thank you for joining me on this journey. And I'm hopeful to do some more streams like this one where we can work on data visualizations and general data exploration concepts, hopefully with Streamlit, because I'm having a pretty good time checking out this tool. So anyway, thanks for joining me on a Saturday, and I will see y'all later. Pull this up.